The wonderful topic of mechanics. One of the reasons we like Newton is these laws of motion, which basically controls all of this mechanic stuff. And the first law, I'm sure you're very familiar with it, even though you might not be familiar with it in Latin, but that is the first law. I'll do a translation for you. There we go. Everybody continues in its state of rest or of uniform motion in a right line unless it is compelled to change that state by forces impressed upon it. So what on earth does that mean? It simply means if I'm standing here, I'm going to stay standing here until something pushes me, something like that. Some force has got to push me to make me move. But in a similar vein, if I'm just moving at a constant velocity, I will stay moving at a constant velocity unless some force is applied to me. Now, it might well be friction or something like that and it slows me down. That's basically law one. Law two, probably the most famous of them all. Motus proportionality. The change of motion is proportional to the motive force impressed and is made in the direction of the right line in which that force is impressed. So when they say the right line, they're basically talking at 90 degrees, at right angles. What does that mean? The motive force is proportional to the change in motion. Well, motive force, change in motion, that's acceleration. So we're saying it's proportional to acceleration. Well, we know if something is directly proportional, then it's equal to a constant times that thing. So we now know that force is a constant times acceleration. And this is where we get mass from, because that constant is mass. So force is mass times acceleration, which then brings the third law up, probably one of the often misquoted of the three laws. To every action there is always opposed an equal reaction, or the mutual action of two bodies upon each other are always equal and directed in contrary parts. Often quoted as to every action there's an equal and opposite reaction. Yeah, it's kind of true, but it doesn't necessarily explain fully what the third law is talking about. And one of those ideas is, here I am standing on the ground. Now we know gravity, the force due to gravity is acting on me at the moment, yet my knees aren't buckling, I'm standing here quite successfully. Because you see, my body is putting a force on the ground, but fortunately there is an equal force of the ground on my body. And they're balancing each other out, and hence I can stand here quite nicely without my knees buckling and so on. That's the idea of the third law. Vectors and forces then. So let's bring together, we talked about vectors. How does this apply to forces? Because forces are vectors. They are vectors. So any force then that is not vertical or horizontal, what we will do is we'll resolve them into vertical and horizontal components, because you see, we're working with straight line motion. That's very easy to work with. It's when we're not going in a straight line, like the projectile motion, we had issues. And that's why in projectile motion we said, no, let's break it up into a horizontal component and a vertical component. What we're saying is we'll do that with any type of motion at all, not just projectile motion. But the original force then will always be the hypotenuse of a right angled triangle, the horizontal motion and the vertical motion. That means we end up with these things called resultant vectors, or resultant forces, if you like. And it's the sum of all the different vectors or all the different forces acting on the body at a particular time. So the resultant force itself is not an actual force that's happening. It's the result of all the forces that are happening. Here's a little example here. Here's my body there, and I've got two forces acting on it, one at 3 newtons off at an angle of 60 degrees, another one 5 newtons off at an angle of 15 degrees. I said, well, overall, what's the resultant force would happen on this body? So here it is. Well, I could think of it like they're just vectors, and we know that we can add vectors head to tail and we get the resultant. And I could do it that way. bit of work, but I could work out the angle there, some geometry. I know that's 135 degrees, and that would now allow me to find the length of this force with the cosine rule, and I could also find that angle. I did that bit first, but I can find that angle using the sine rule. So sine theta over 5 will be sine of 135 over that force there. So 5 sine 135, well, the angle turns out to be 28 degrees 41. How did I get force R? See, I knew I should have done that one first. Huh? Okay, maybe I just got the order wrong. But the magnitude I can work out with the cosine rule, so 3 squared plus 5 squared minus 2 times 3 times, etc. There's the 7.43 that I then used in the sine rule to get our angle. That's a lot of work. And that's why it's easier to go, no. What we're really doing is vector projections. We're projecting the vector into the horizontal and the vertical component. So that 3 Newton force I could think of, there's a vertical one that goes up and then one that goes to the right. Bit of geometry, I know that angle's 60 degrees. And the 5 Newton one, I've got one going to the right, then one up. And I look at just the vertical ones. So vertically I've got 3 sine 60. I know it's the sine because it's the opposite side to the angle I'm referring to. And I've also got this one of 5 sine 15. Horizontally, I've got 3 cos 60 and I've got 5 cos 15. So together, if I just look at the horizontal components and also the vertical components, then there's my vector. I can now just draw, there's the resultant vector, but just one nice right angle triangle. I don't have to use the sine rule, I don't have to use the cosine rule. I can just do it with one nice, neat right angle triangle. So the magnitude, the length of the hypotenuse, surprise, surprise, there it is, 7.43. A little bit of trig, tan theta, and there's the angle. Makes life a lot easier. Just looking at forces at right angles to each other. So what are all the different types of forces we might encounter? The big ones are resistive forces. So whenever a body moves in a medium, so through the air, through the water, whatever, it will be subjected to a resistive force in the opposite direction to the motion. So if you're in the air, it will be air resistance and things like that. Now that resistance is usually proportional to v, or v squared, but some component of the velocity kind of makes sense. The faster you're going, the more resistance you will get through the air and things like that. So you always find that that resistance is going to be proportional to v or v squared. And the other one that we see a lot of is gravitational forces, also called weight. So the force of attraction of the object from, well, we're talking about the Earth here, but I mean anybody, it could be on another planet, so you still got a gravitational force, is the force of gravity, force due to gravity. And we know that to be mg, force equals mass times acceleration. And at the surface of the Earth, we accept that, gravity is around about 9.8. A lot of times we round it to 10 to make the calculations nice and easy, or just leave it as g, so mg, that's force due to gravity. But forces will appear in pairs, and that's to do with third law. Because remember, me standing on the ground, I'm putting a force on the ground is putting a force on me. The forces appear in pairs, but they'll be of the same magnitude and in opposite direction, for instance. So these things called normal contact forces. So anytime you have an object in contact with the surface, so it's like me standing on the ground, there'll be a force the other way around. So me on the ground to me. And that's called the normal contact force. We usually just say the normal force. We also then have frictional forces. Why do things stop when you roll them along? Why don't they just keep rolling? Because there's friction that's slowing it down. So when an object slides over some fixed surface, there'll be a frictional force. Now it does have some limiting value. Right? Magnitude, it can't exceed a certain amount, and it is always in the opposite direction of the motion because it is a resistive force. It will usually be some multiple of the normal force. Okay, so there'll be a mu, which we call the coefficient of friction, times the normal contact force. So we usually find that sort of thing. Then the next force, tension. It's the other ones we look at a lot of. So whenever you have a string, well, we say a string, but it could be a chain, it could be anything. But it exerts forces of equal magnitude on objects attached to it. And those forces will always go along the string and away from the object you're working with. So the magnitude of the force we call the tension in the string. Whenever we're solving a problem, don't get hung up with up has to be positive and to the, hang on, which one is that? To the right has to be positive. You can set positive to be any direction you like. And usually we just say, well, whatever direction we're traveling in, we'll make that positive. That's going to be my positive direction. And then resistance then will always be in the negative direction. It just makes life easier. But the other key thing, and I know you hate drawing diagrams, I don't know why students hate drawing diagrams, but it makes life so much easier. Always just draw up a simple diagram of your forces and it will make life so much easier when you're solving these problems. Let's have a look at this. We've got a box of mass 32 kilos. It's got a handle on one side, but two people are trying to move it across the floor. One person's at the front, one person's at the front. They're pulling it horizontally with 20 newtons. The other's pushing it from the other side with a force of 25 newtons, but yet the box does not move. Draw a diagram of all the forces acting on the box. So what are all the different forces? Okay, there's good old Bob. That's what I always draw for the object, just a simple dot. Okay, what have we got acting on it? Well, I know there's a force, that person's at the front pulling it. So I'm taking to the right to be the positive direction, and so there's a force of 20 going that way. But then there's also someone pushing it, but that would also be going in that direction because they're pushing it that way with a force of 25. What's stopping it move? Well, it must be friction. There's some resistive force stopping it from moving, and resistance is in the opposite direction. So that I'll just call it F3. It's the friction. But there are actually other forces acting on this. There is still the force due to gravity. But that means there's also a normal contact force because this box is on the ground. And the box is not being crushed through the ground, so the normal contact force must be there balancing out the gravity. So technically there are 5 forces involved in this problem. Now we might not have to use all of them, but it has said draw all of the forces. Well, they're all of the forces that are in this problem. Now it wants us to find the frictional forces. So for this problem, to solve this, the vertical ones are totally irrelevant because I can find the frictional force by just working horizontally here. So what is the resultant force horizontally? And you'll note I use Newton's notation rather than writing d2x to t2 x double dot. It's quicker. Now mx double dot is the resultant force, and I'll set my resultant force to be in the direction that I'm traveling. Notice I don't put the resultant force on the actual force diagram because it's not a force. It's the result of all the other forces. It doesn't go on the force diagram. What is the sum? Well, I've got force 1 and force 2 going in the positive direction. I have force 3 going in the negative direction. But there's another piece of information. Remember, the box does not move. So the result of all these forces is 0. It's like nothing is happening. It's no different to if I just left it alone and did it there. The result of everything is nothing. So I know all those horizontal forces are equal to 0, so I can sub that in as well. Now it's just a matter of rearranging a very simple equation, and we get that force 3, our friction, is 45. There we have 45 newtons. There's our problem. Okay, let's make it a little bit more interesting. So we have 2 trucks here. The one on the left's got a mass of 20 kilograms, and the one on the right 50 kilograms, and the truck on the right is pulled along with a force of 120 newtons. Now, neglecting friction. So, all right, we're going to assume there's no friction in this one. We want to work out the tension in the chain that's drawing these, or joining these 2 trucks together. And you'll notice that both of those tensions are T because it's the same chain. So the tension must be the same either way. Because if it wasn't the same, well then the chain wouldn't be tight. It would be slack and it wouldn't be pulling along. Let's just look at the 2 objects individually. So I'm just going to look at the left truck. What's happening with the left truck? I'm not going to worry about the vertical forces for this. because again, everything's horizontal here. I don't need to worry about the vertical forces. So horizontally, the only thing that is happening is tension. It's the only thing, because we're neglecting the friction. So on the left one, the resultant force is purely the tension. mx double dot is T. But force is mass times acceleration. I don't know the acceleration of the truck, so I'll leave it as A. But I do know the mass of the truck. So I can say, well, 30A is T. I know that. So there's my acceleration. Whatever the tension is, divided by 30. Let's go and have a look at the right truck. Now, what's happening with the right truck? It also has tension, but it's going to the left. That is the linking force between these two, which will allow us to go and solve the problem, find the tension. The right-hand side, bang, 120 newtons going to the right. So this one, and I've changed the pronumeral because is the acceleration the same? Maybe it is, maybe it isn't. Is equal to 120 minus the tension, but yes, the acceleration would be the same. Because if the only thing is that they're joined together, it's like they're going to be moving with the same acceleration. If they weren't, then that chain would go slack and you'd no longer have the tension in there. 50A will be 120 minus T. Well, if I substitute in what I know A to be over here, T over 30, I've now got an equation where I can find what the tension is. And we get T is 45. And so there's our tension, 45 newtons. Now the units for force, newtons very often used, but the other one is kilograms meters per second squared. Why? Because it's mass times acceleration, and the units for mass is kilograms, and the units for acceleration is meters per second squared. A mass of 2 kilograms resting on a smooth plane, inclined at 30 degrees to the horizontal, connected to a mass of 4 kilograms by an elastic string which passes over a pulley. Draw a force diagram of the problem. Here's our two masses. This time I've put it on the plane, some pulley joining the two together there. Over here on the 2 kilograms, well, this one is in contact with the surface. So therefore I know there's going to be a normal contact force and perpendicular to the surface. It also would have gravity. So the force due to gravity would be mass times acceleration, in this case 2g. Over here on the other one, it's also got gravity, but hey, we've got this string joining them, so there'll be tension up the string on the right one and up the string on the left one as well. Now, they haven't talked about friction in this one, and the fact that they've said a smooth plane, it's sort of implying to me we don't have to worry about friction in this problem. So I haven't put friction in there. Here's my force diagram. I've drawn all the forces on the two different things. Find the tension in the string if the 4 kilogram block is moving down. Let's have a look at that 4 kilogram block. What's happening? What are the forces? Okay, 4G was going down, tension was going up. That's pretty much it. So I'm going to say force of R4. Now, why did I call it R4? Because it's the 4 kilogram block. So, I'll call it 4. 4 times acceleration will be 4g minus t. Let's go have a look at the 2 kilogram mass. Now, 2g is going directly down, tension is going off at an angle, and that normal contact force is going off at an angle as well. I'm going to resolve, but I am not going to resolve the tension force and the normal force. It's actually gravity I'm resolving. I want things to be at right angles to each other. You see, I don't know the contact force. I want to get it out of my problem. So if I treat force 1 as if it was the vertical, if you like, and just look at the forces not vertically and horizontally, but down the plane at right angles to the plane, then when I look at the forces down the plane, I don't have to worry about this contact force that I don't know anything about. I can just deal with the things, well, T is the one I want to find, and this other one here is the component of gravity which I know. That will make life easier for me. The only thing I have to work out really is where is the angle in this? I'm playing around with geometry because, oh, well, that would be the 30 degrees there. So you play around with geometry to work out where exactly is the 30 degrees they gave me. Remember, the resultant force will turn out to be the hypotenuse. So because I'm resolving the gravity into the two components, it's the hypotenuse of a right angle triangle. So these two end up at right angles to each other. Okay, So I'm just going to look at forces up the plane. If you want to tilt your head, you could say, oh, the horizontal forces. Looking at that, I've got tension, and then I've got the component of gravity. It's opposite the 30 degrees, so it must be sine 32G, sine 30. So I now know the force on the 2 kilogram block is equal to T minus 2G sine theta, because remember it said that the 4 kilogram block is going down. Well, if it's going down, then the 2 kilogram block must be going up, and I'll make that the positive direction. So 2A is equal to T minus 2G sine theta, sine 30. Okay, now I can substitute that into my first one. Sine 30 is of course a half. Alright, playing around with that, we get T equals 19.6 newtons for the tension.